Okay, so asymptotic logical uncertainty in the Benford test. So there's a lot of authors on here. I'm not, in fact, Garrabrant. I'm Lloyd, this last author here. I'm a PhD student at UCLA. And while I have this slide up, I just like to take a moment to acknowledge. Can people hear me in the back? Sorry. Okay. I'd like to take a moment to acknowledge that and thank Miri for, one, getting all these people in the same room, and two, being kind enough to send me to this conference. Okay. So, a brief overview of the talk. First of all, what the heck is logical uncertainty? Briefly, this is a formalization of mathematical intuition. And so I'll motivate, I'll do some motivation of this and do injustice to the related work in this area for a lack of time. And then the meat of the talk will be, I'll attempt to explain our approach to this problem. It's based on pseudo-randomness, and so we have an operationalization of that, and also this proposed test that will be related to our definition of logical uncertainty. And finally, if I have time, I'll briefly outline how our algorithm accomplishes this. Okay, so logical uncertainty, briefly, is a probability over logical statements. Now, I put this in scare quotes because this ends up not being very interesting if we obey all the axioms of probability theory, right? Things that are true have to have probability 1, things that are false have to have probability 0. And that doesn't seem like a good capture of mathematical intuition. So instead, one way to look at this as a seed of belief for some conjecture, something that hasn't proven true or false yet, but that we have some knowledge that it's probably more likely to be true than false or something like that. A sort of second flavor of that actually could be guessing the outcome of a computation that we just haven't had the time or resources to actually do yet. So for an example, the first type, I might say, P versus NP is sort of this long-standing conjecture. It's believed to be false, that the two are equivalent in complexity theory, but we don't know that yet, so we can't say that's true or false, but yeah. I think that there would be objections if I had said this was 99% right. That's not something that we think is going to turn out being true. So if I say that this probability is 10%, well, one way to look at that is maybe I'm saying I'd be significantly more surprised to find out that there was a proof that this was true than to find a proof that it was false. And possibly, if you have some logical uncertainty system and it makes a lot of statements of this type, maybe I can measure its calibration, and if it says that something has 10% probability, then 10% of those turn out to be true. Okay. On this talk, we'll be focusing on sort of the second flavor of logical uncertainty, and that is the outcomes of long computations. So there's a certain sense in which, yes, the Google digit of pi has some definite value, but we don't know what it is yet. And yet, if you were forced to bet on it, then it seems to make sense that the odds you would give would be 10%. And so to formalize that, we'll be treating sentences like this as elements of a pseudo-random sequence. Okay. So to briefly summarize some of the related work, the main reason that standard probability theory doesn't work is because of this problem of logical omniscience. This was a term that it goes back at least to Parik in 87, I believe. And this is based on the problem that in order to have a consistent probability distribution, you need to know all the logical consequences of your beliefs. So for example, if two sentences are equivalent, you must assign them the same probability or you'll be inconsistent. It's actually hard to know that two sentences must have the same truth value. So one way around this, of course, is to relax this constraint. Consistent will just sort of not care that some of our probabilities don't make sense. There's also other approaches that will sort of eventually converge to a consistent probability distribution. Okay. And of course, see sections 1 and 2 for a much better treatment of this. Okay. So moving on, in order to operationalize this notion of pseudo-randomness, on which our logical uncertainty will be based, we'll pick some formal logic. In the paper, it's ZFC, right, standard set theory. And in this system, you can enumerate all of your sentences and give each of them a number. And so pseudo-randomness will be relative to some time bound, right? This is our time constraint. If we had enough time to compute these things, of course, we could get them exactly, but this is formalizing that notion of having enough time. And so, in order to define these classes of sentences that I mentioned earlier, we can use Turing machines to do this. So we can point at an infinite subset of our logic using a Turing machine, sort of define this nice and computable way. We give a time limit on this Turing machine, and then if it halts within the time limit, we'll say that that sentence is part of our set. And so, in this in this way, we will define pseudo-random sentences as sentences that are decidable in our logic, but that we don't have enough time to compute. And so, to give a little bit more of an intuition of that, right, we're talking about sequences of sentences that are decidable in ZFC, but, and so there's sort of this binary sequence where if they're true, you get a 1, there's false, you get a 0, but that we can't define a simple Turing machine that will do better than chance at guessing those. And I'll formalize all of the things that I just said there on the next slide. So more formally, we can pick some way, some universal Turing machine, and relative to that, some description length of Turing machines, and look at their behavior. So, and this will give us our test for pseudo-randomness. So if we run some random Turing machine for up to the time limit, we can interpret that as getting a subset of our set of sentences. And sort of a similar way to what we did before, we'll just give it a time limit, and then if it halts at a 1, then that will be considered part of our subset. And so we can define sort of an empirical frequency of the true sentences in the subset by looking at the smallest m members of that set. We'll get a frequency of which of those turn out to be true. Okay, and we can use this, the claim is, to test this sequence, the larger sequence of which this S prime is a subset for pseudo-randomness. So we use a result from statistics called the law of the iterative logarithm, and that will give us a bound that holds almost surely for any random sequence. And it will be based on our sample size, right? So we can test this, we can increase m and test this for different sample sizes and see whether this bound holds, and that will tell us whether this the sequence is random or not, or pseudo-random. Right, and I mean, this is a sort of a standard result, but it's worth noting that we've added this K of W term for the simple reason that a Turing machine could just encode, right? We're looking at all Turing machines, so in linear time, you could there exists some Turing machine that encodes the sequence directly, and that's not particularly interesting. So that's where that term comes from. Okay, and then to formalize this notion of pseudo-randomness, we call this an irreducible pattern. Right, there's no simple Turing machine that can encode this sequence. And it must hold for all Turing machines that meet this complexity bound. Okay, so for example, we could construct the set of sentences that refer to all the digits of pi. We want to make sure they're a little further out than merely linear in time, because there are linear time algorithms for computing digits of pi. Right, so we want to make sure that it's something that we haven't computed yet. And this has to be conjecture, unfortunately, because we don't yet know that there's not like weird patterns really far out in pi. But assuming that there aren't, this should be an irreducible pattern, and we get a probability of 10% for any particular digit if we haven't had time to compute it yet. Or for second example, this is using New's up arrow notation, right? If you're not familiar with it, it's not terribly important except that it grows incredibly fast. We are unlikely to ever compute the third element of the sequence. And yet, we would expect, because this is a subset of the powers of 3, and powers of 3 are known to follow Benford's law, that we should get this sort of more interesting than 1/10 probability of log base 10 of 2. Okay, and so that's where the Benford test comes from in the title. And so we want to have some sort of general way to find these patterns, right? We could hard code this in pretty easily, but how do we find all such patterns? So the generalized Benford test sort of formalizes that thing we want to capture all such patterns. Right? It's based on Benford's law that applies for digits 1 to 9. And so we designed an algorithm that can output probabilities on any sentence. And furthermore, it does this in an amount of time that is relatively close to this t event. Right? It shouldn't take too much longer. We can do it with a sort of additional factor of n to the 4th log. But anyway, so you know that we don't have enough time to actually compute these things. And the generalized Benford test says that for all irreducible patterns, we should convert the probability that we assigned to that sentence, to sentences in that irreducible pattern, should converge to the true probability of the irreducible pattern in the limit. Okay. So our general strategy for doing this is going to be find a reference class for any sentence that we want to give logical uncertainty on. So example reference classes are the ones I mentioned before, all the digits of pi or all the powers of 3, or the first digit of the powers of 3. And we'll also make use of a theorem prover to get sort of a sampling of how many elements are true or false in these patterns that we're testing. So we can construct a Turing machine that does this. It will halt pointing at a 1 if the sentence is proven by our logic, halt pointing at a 0 if it is disproven by our logic, and otherwise will not halt. And so our strategy is going to be, essentially, we're going to look at pairs of Turing machines where X is going to attempt to find the best irreducible pattern for our sentence, and Y is going to try to refute that by finding subsequences where the assumption of randomness doesn't hold. So if S is this set where both of our Turing machines accept the number, then we'll generate a sample by running our theorem prover on every sentence in that set, and that will give us, one will give us a number of sentences, a sample size, Q of n, right? That's the number, because the thing might not halt, and in general we might get sentences that aren't decidable. We're restricting to those ones that we were able to decide quickly. And then we have a sort of empirical frequency of the sentences that turned out to be true. And so basically, our algorithm optimizes this objective in a particular way. So this is worth explaining in a little more depth. So the main term is this. This is sort of the reciprocal of the thing we saw for the iterated logarithm earlier. Essentially, right, so this is the deviation from the observed frequency from the frequency p, which we're trying to guess, relative to our sample size and the square root of the sample size and the log square root of the sample size, and then of course the complexity terms come in again because we could just encode the sentence directly in linear space. Okay, so formally, that's the gist of this, and formally we're computing this optimization where we're minimizing over x, maximizing over y, and then picking the best rational probability based on this objective. Right, so rational in the sense that we have the denominator depends on n. And right, these Turing machines must be Turing machines that accept this sentence because we're looking for irreducible patterns of this particular sentence. And this passes the generalized Benford test. I won't go into too much details of the proof, but basically, when we have a Turing machine that enumerates a true irreducible pattern, we'll get a constant upper bound for our objective, and that will imply that as we run this for more and more sentences, we'll eventually converge to the correct probability for that pattern. Okay, so to briefly summarize, because I'm out of time, we have this. We have a type of logical uncertainty that Benford's law points at. It's based on the sequences of sentences that we don't have enough time to compute. We can use the law of the iterated logarithm to get a test of randomness that we throw many Turing machines at, and that will locate a reference class for any particular sentence. And that will give us logical uncertainty over every sentence in our logic, but unfortunately, we can't really say much about how coherent this distribution is going to end up being, and so in future work we hope to merge these two ideas together. Okay, thank you.